Remotely Attacking System Firmware. Jesse y Michael demostraron una vulnerabilidad en la característica de actualizaciones vía Internet de los sistemas UEFI que puede ser utilizada para instalar software malicioso, ejecutándose en el nivel de privilegio más alto, evadiendo los sistemas de detección de seguridad e incluso sobrevivir a actualizaciones del sistema operativo.
We want to present something really new, a remotely attacking system firmware, something really special for us because we have reliable exploit for this research, which is we're really proud to have. The work was done by 3 people, myself, Jesse, and Mickey. Mickey couldn't make it here because he is now in Blue Hat, trying to understand what this new APT28 UEFI implant is doing, and how interesting it could be for us as a community, as an industry, to detect this type of threats, to understand this type of threats, and so on. I will a little bit mention this during the talk. So over the talk, we'll go over some of the basic things, some of the fundamentals. We'll talk a little bit about how much different remote interfaces we have nowadays in the low-level components like firmware, system firmware, BMC, and so on. Then we'll go over the remote attacks on specific component and specific feature in some of the vendors, which we will find vulnerability in. Then we'll walk through the exploit, and we'll talk a little bit about why it is important to care about that. So, if you're talking about any technology stack, we're always thinking about like user mode applications like browser, Office, and we want to make sure that it is updated, and we know there is a bunch of good security done in these 2 layers, in the user mode and the kernel. So we know that there is a lot of exploit mitigations was implemented. There was like internal team doing validation. There's bug bounty programs, and we think there's like industry make a really great job here for the last 10 years. To create the attack from the browser to the kernel, you need to chain a bunch of bugs to the vulnerability, to the exploit chain to compromise it. So, but in every technology stack, there is a second part, which is hardware. And from the server to the desktop, to the laptop, to ATM machines, to AVI system in the car, and so on. And usually we think about hardware as a monolithic trusted block. So we don't think that's supposed to make any security problem for us because we buy the hardware from vendors. We believe the vendors did great job to protect our hardware. Same as for the user mode. We assume that security of the hardware is very well done as security, for example, in the browser. But what happened in the last decades is the hardware become much more complicated, and the vendors is trying to do some job, but they still have a bunch of things to do. So this is the example of the low-end server motherboard. And if you think about that, every server nowadays has a bunch of components. Like it could be between like 10 and 15 different components from different vendor, from different timestamp collected to build the motherboard. And these components in many cases may run a software, call it the firmware. And this firmware can be outdated. It can be compiled without security mitigations. It could be, in some cases, vendor even may not have a source code of that because it was just too old. In some cases, the signature, the update may not be signed, so attacker may use legitimate interface to update the firmware and compromise the system and compromise this specific component. In many cases, that component doesn't have a read interface, so you cannot like run integrity on that component. And in many cases, that components has the interfaces to compromise the other components and entire system. For example, there is a DMA capability which will allow components which has this capability could compromise the host of the system, like a victim operation system, like extract the secrets from the memory and so on and so forth. So this is telling us the serious blind spot which we have right now in a technology stack. And if you think about, there is a 2 type of attack which usually we consider to low-level components. One is the attack with physical access. So if someone has the physical access to the laptop, desktop, or server, they can do something. They could attach programmer to some of the components, reprogram the elements. And you think about this, it sounds like complicated. You need to do, and you need to have a bunch of knowledge. We demonstrated this year that it has taken less than 5 minutes to infect any enterprise laptop with the physical presence. with open source implant, which makes this attack even more simpler. We did it for research purpose to demonstrate just how easy it is to compromise systems with physical access. And multiple technologies doesn't make any prevention from the physical access. But there is not just only physical access. There is second part, and there are second sets of area for the attacker is software attacks. Attacks which is initiated from the software perspective. So neither someone running already in a system from the operation system, and it try to compromise more low-level components to get a persistency and stealthy, to make it invisible, to make it in a level of privileges that will survive for installation operation system, re-imaging hard drive, replacing hard drive, and even update your BIOS. There is type of malicious malicious samples which could survive even update of the BIOS. And if you think about the software threats, there is two categories in the software threats. One with the local privileges, which is like you can say, yeah, I would assume if someone compromised already my system, then I don't need to, this is game over already. But there's second type of the software attacks, remote attacks. And you may think about, yeah, but the firmware is not supposed to have any remote interface. So in theory, firmware is supposed to be like something isolated, which doesn't need to have that its entire network stack. But in reality, it is different. And we know multiple examples when the firmware and in some of the hardware components has entire implementation of the network stack, which is fully independent from the OS, which could be compromised separately, which is working separately. And there is a couple of them. One example is the BMC one. So BMC is a baseboard management controller, is the part of the management capabilities in any modern server. So any server has it. And even before you press the button, but after you plug the power to the server, this component is already running. And this component has already its own network stack, which has its own MAC address and already send the traffic even before you press the button on your server. This technology even works if you don't have CPU, if you don't have memory. You still can boot BMC and you still can use BMC capabilities in your server. And it has its own CPU, it has its own RAM, it has own storage, so it's fully dedicated small computer inside the server, which is running even before the main CPU it starts up. Why we need these capabilities? First of all, it is management capabilities. So in many cases, you want to have remote KVM, you want to remotely install operation system, you want to remotely update your BIOS, you want to do a bunch of things remotely. And how you can do it if you have a data center with thousands of servers? You use these KVM capabilities. You provision BMC automatically, and then you use all of these capabilities. But also, it makes the huge blind spot for the attacker, and it may have its own vulnerabilities in implementation. So if you just run like scanning of the BMC port on the BMC interface, you will see that the BMC has its own web server, like fully implemented web server running separately from your computer even before your computer starts. So any vulnerabilities there may allow you to have an access before your computer starts. And because BMC is staying in a really sensitive buses, it also has the DMA capability, it has the spy access, so it could fully control the system from that point of view. And we have a separate talk about this tomorrow. If someone wants to get more details, we will explain more details tomorrow. I don't need to stop it today for long. So, and if you think about the BMC, it's not just only Ethernet interface. They also have a bunch of other interfaces supported by a standard, which is also the opening another attack vectors for the attacker. So they can reuse different capabilities like serial capabilities and other capabilities accessible for the BMC. This is implementation dependent. So not every typical server may have multiple capabilities, but usually the basic capabilities over Ethernet is available for any server. So if you'll take a look a little bit in history, so the first BMC standard, BMC IPMI standard, IPMI is sort of protocol to communicate to the BMC, was released in 1998, and that one didn't have any network capabilities. So they released the standard for management, but without network. And it was pretty good in security perspective, but really bad for usability perspective because people couldn't use it. And then they start granularly adding the different new capabilities, including network management capabilities, including different protocols, IPv6, IPv4, and so on. And then, until 2013, everyone didn't care about security of that components. But there was really good initiative started from 2013, and up to these days, and even today, there was immunity. And Nico from Immunity presented the attacks for the BMC, for the Dell system. So from 2013 until now, there is like at least 5 major research was presented, which was compromising BMC over different interfaces, including remote one, and including remote without authentication at all. We will talk about that tomorrow a little as well. So another component which has its own network stack and also the part of the attack surface is MEMT. This is sort of similar to BMC, but for desktop. So for desktop management capabilities, Intel released that nice technology. This technology has its own. This technology was implemented in a chipset, and it is also has its own CPU, its own memory, its own storage. So it is the small computer which is running in any desktop, vProsQ, which could provide the remote capability for the management, for the IT management, and also is the part of the attack surface for the attacker. If you scan the port for the Intel MTME technology, you will see that it also has HTTP, HTTPS, and all of that. Interestingly, that in BMC, in NME, if you would connect to HTTP, it will not redirect it to HTTPS. So that's only your choice to pick and secure protocol to communicate to this technology. And if you take a look in the history, there was similar dynamics. So first, they released technology without much network capability. There was some network capability, but not much network capability. In 2010, Intel added KVM as a part of the functionality to the IMT technology. And then 7 years later, there was really interesting research initiated from multiple different companies showing multiple different vulnerabilities in IMT technology, including bypass authentication with empty password, including memory corruption over just buffer overflow in some of the ME-ROM code, including even debug MEMT chipset over some of the debug capability which is Intel provides for pre-production system. There was a lot of interesting research and showing us that this is really practical attacks. Also, in 2016, there was a Platinum campaign. There was in a wild attack which is heavily used at MEMT technology. So a couple words about that. MEMT technology has something which has a state, and that state could be disabled or enabled. But when the state is enabled, it also has two other options. It could be provisioned or not provisioned. So if it is not provisioned, it's ready to be provisioned any moment. And anyone with physical access can provision it over USB or from the ring 0 over admin privileges. If it is provisioned, it's locked down. So meaning that someone set up the password for the web, from the web interface, someone set the configuration, and no one else could do it. So if the system is not provisioned, it basically allowing attacker reuse these capabilities to provision itself. So attacker know that, okay, this system now is enabled and it is not provisioned. I will provision it and will use this capability. This is how does the Platinum will use it to build a really stealthy communication channel to the CNC server over the provision IMT which the attacker provision itself, and use the serial over Ethernet capabilities to send traffic fully bypass the firewall in the system. So, and then also we know that there is a system firmware. We know that system need to boot somehow. So, and there was a BIOS. In other words, a system firmware is responsible to boot the system. The system firmware has two components: runtime component and boot time component. We know that the system firmware running from the SPI and it's stored in the SPI, and we know it's running in the main platform. And typically, if you take a look in history, we don't think too much about network interfaces to the system firmware because we believe it doesn't need to have it. But if you take a look more deeply, in 2007, they start adding some of the network capability. If you remember, there was like a Pixie boot when you try to boot over the network. So that is a little bit network capability. And then they added more capabilities, which we will talk a little bit later, like Wi-Fi, Bluetooth, and so on. And you may ask why we need network capabilities in our system firmware, in our BIOS. Like in the most trusted code in the platform, why we need the network capability? Again, because of the management. The vendors want to increase the management capabilities, and this requires them to implement entire network stack, including some of the features like update over the internet, including like Bluetooth keyboard and mouse, and so on. So from the standard 2.4, the entire reference implementation of the network stack was done to UEFI-based BIOS, meaning that from that point of view, any BIOS which was baked in the platforms has the network stack. From the from the IP, IPv4, IPv6, TCP, HTTP, HTTPS, DHCP, FTP, and all of that protocols. And all of them was implemented from scratch. So meaning any vulnerability in that protocols will allow attacker to run the code even before the OS will boot. And then vendors start building more technology on top of it because they want to extend the stack. So some of them built entire RESTful API on top of already existing network stack, which was built before then by Intel in a reference implementation. So the stack is growing. And then it's growing hugely. Vendors like IMI implement Bluetooth stack. So if you play with your setup screen from the Bluetooth keyboard and mouse, that Bluetooth stack is working only because the system firmware implements this Bluetooth stack. And the interesting one that it's supposed to enable by default and supposed to enable and scan it, the devices in the Bluetooth capability. So any vulnerability, remote vulnerabilities there make a game over for entire compromise of the system. And we found that that stack also has SMM components, so the components which is running in the most privileged mode in the system. Then we also figure out that there is a Wi-Fi stack there. So again, IMI implemented the Wi-Fi stack, so even before operation system starts, already customized Wi-Fi stack is running and scanning and looking for the networks. And as we know that I already mentioned a little bit, some of the BIOS implemented Pixie functionality, which could be done differently, depends on the architecture. If it's running from external device, it could be done from option ROM. It could be done as an internal Dixie driver. But these capabilities exist, basically. You can boot the system from HTTP or from a TFTP. You can boot the operation system from there, which is also giving the attacker good level of privileges. And based on all of that nice technology, vendors start building another features. For example, this HP intelligent provisioning system is the system which is allowing to download and run different software in the context of your BIOS from the HP side. So meaning that if you're enterprise, you have the root of trust fully to the vendor's website. So if someone compromises vendor infrastructure, then they could compromise all of the system which is using this technology. So meaning if you're in enterprise and if you have HP server and you didn't disable this technology, inside your trusted boundary you have entire infrastructure of the HP. Plus, if the HP for some reason delivers some vulnerable binaries, it also could be running in your BIOS, in the BIOS of the enterprise. Another interesting feature was SMTP, so you can send emails from your BIOS. So even before the operation system boots, there's a capabilities which you basically can use to send email. And you may ask why they need it. Because of the diagnostics. There was a nice example how to build diagnostics over SMTP. So you can attach any file and send it to some random email from your BIOS before operation system boots. It has entire access to the file system because it's loaded its own NTFS driver. And then remote diagnostics. There is another feature which is accessible for the HP for running diagnostics on the system for the desktop and laptop. This one is pretty interesting because you can schedule this time to time, and then it will scan the remote server, and if it will find that URL, that will try to download diagnostics tool and run it. So pretty dangerous functionality as well. And finally, we arrive at a really interesting area when the vendors start implementing the technology which they call it update over internet. So basically, they try to update the BIOS from the internet. How does it work? In the most privileged level of the system, You connect into the remote web server, you download the binary, you download that binary in the system, you unlock fully your system because you only can deliver the BIOS update if the system fully unlocked. And then when you unlock entire system, you run this update. So imagine this, in the most privileged level in the system, you connect into the web server, downloading some binaries and running the binaries. And that's pretty interesting. And what could go wrong with this technology? Jesse will continue and will show you a couple of interesting things here.
So thanks, Alex. So as Alex mentioned, the system is fully unlocked at this point. There's no spy write protection because as part of the update process, it needs to be able to write that firmware image back to the spy, and none of those locks have been set in the system yet. And here's an example of one of these functionalities in an ASRock BIOS. Here's one in ASUS. It's essentially the same thing. They just completely wrote their own implementation because there's a reference implementation for UEFI BIOS called Tiana Core that they basically create a complete implementation of the specification as it stands, but vendors basically want to create their own functionality on top of it. So all of these update over the internet, all the features that Alex was just showing you are all created by vendors and don't have that same level of review that the reference implementation has. HP has their own functionality to do the same thing. This could be scheduled where every reboot, it'll go out and automatically check. You can set your BIOS source so it doesn't go directly to hp.com, but you can have a custom URL that it'll go out and grab its configuration file and BIOS images from. And we did, as part of our analysis, we discovered that both ASRock and ASUS are both vulnerable to just basic stack overflows as part of this update mechanism. They both use just plain HTTP when they're going out to the internet. There's no encryption, no certificate checking. It's easily exploitable by man-in-the-middle or poisoning, doing DNS poisoning, route poisoning, other mechanisms to interfere with that communication with the remote server. So here's what ASRock did once we reported this vulnerability to them. They basically realized that essentially all of their models from Haswell onward were vulnerable to this, which was around 300 different motherboard models, and they basically created new updates to disable this functionality. They didn't remove it, they just disabled the ability to actually trigger this. When we told ASUS, they basically just didn't really understand why it was a problem and why they should fix it. So ASUS did not actually fix this problem. And as you can see, they say it's only an issue before the OS loads, so it's not a problem. And we went back and forth with them a little bit and tried to explain, no, this really is a problem. You guys should fix this, but they didn't understand. So here's an example of what the ASRock update mechanism request looks like. As you can see, it's just plain HTTP web request to asrock.com. It's just an ASP page that includes the model of the particular motherboard. So if you do a man-in-the-middle and get the motherboard, you can deliver a specific targeted exploit for that particular motherboard. Here's what the response looks like. It's basically just an XML document with some URLs and description of what different BIOSes are available, description of the BIOS, version, date. So if you replace those fields, it basically shows up like this in the interface. And we discovered that if you just have a really long string in some of these URL fields, there's a buffer overflow. Here's what the ASUS request looks like. It's basically a very similar process where it's also plain HTTP. And instead of having like a specific page where they pass the model as a parameter, they have a path to a particular index file to get that's based on the model instead. So it's a very similar mechanism. It's not quite XML. It's similar, but a little bit different. And they have overflows here also where basically, if you man in the middle of this and modify those fields, when you do the update, it just hangs. And that's pretty suspicious. So In order to figure out what actually is happening underneath the hood, you're going to need a hardware debug interface like one of these. So the old hardware debug interface is the XDP, which costs around $3,000 from Intel. You could only get that if you have an NDA with them, and it also required you to open the case, and there's a physical header that you'd plug it into. It's a 60-pin header. It basically has a JTAG on it and a bunch of other signals. And you could even find this header on production motherboards, and sometimes it's even labeled like CPU XDP or PCH XDP. This is basically, like, these hardware debug interfaces are used to even bring up the chips when they originally manufactured them, as well as once they're shipped to OEMs, the OEMs will use this to develop system firmware like BIOS and get their code to work in the first place. And it's kind of a pain to always have to open the case, plug in this connector to this header on the motherboard. And a lot of times, once they actually move to production, they want to remove the header, not have that functionality there. So they've moved to this newer technology. The kind of stopgap in the middle was this closed chassis adapter in the center, where they basically have the capability to hardware debug over a USB port. So they don't need to open the case. They can just plug in from USB and use this closed chassis adapter to send those special debug signals over USB, which is pretty cool. These ones you can buy for about $300, $390 from Intel, but in this case also you need an NDA with Intel. The center one is really only needed if you're using an old platform to debug a new target that supports this new debug capability and debug over USB. If you're using a system that's Skylake or newer for both your debug host and your debug target, you can just use this cable on the far right, it's essentially a USB 3 A to A cable that has the voltage line removed. And you can buy it. You don't need to buy it from Intel. DataPro has it for $15, I think. And it's pretty nice. But once you have the hardware interface to talk to these debug interfaces, you'll also need the Intel System Debugger, it's essentially like GDB, except over hardware, and you've got some kind of similar functionality. You can halt all of the processors in the system, examine the internal state of the machine, read memory. If you build your own BIOS, you can even do source level debugging through this over hardware. So there's also something called the Intel debug abstraction layer, which essentially there's you can write scripts in Python to do debugging. This is an example of using functionality in these debug interfaces to break on SMM entry. So if you want to debug a system management interrupt, this is the only way that you'll be able to do that. You can also break on a VM exit. So if you're debugging a hypervisor, you'll want to use a hardware debug interface like this. Makes it much easier to figure out what's going on. So for actually, once we discovered that feeding some data to our system will cause it to hang, in order to figure out what's actually happening, the first step we'll do is basically just set a breakpoint on the general protection fault handler. In order to do that, we can use this hardware debug interface to view some of the different CPU structures. You can look at like model-specific registers and all that, but for our case, we just want to look at the IDT, and we can see our general protection fault, those registers, and then we can use the same tool to basically add a breakpoint, and we can have a hardware breakpoint that accesses on, instead of just once code executes here, we can actually have hardware breakpoints on read and writes to specific addresses or read and writes to I/O ports. There's also the ability to add breakpoints on specific system events like SMM entry, VM exit, like I just mentioned. But for this case, we'll set a breakpoint on the general protection fault handler. And when we pass our code to it, we get a fault, and our breakpoint is triggered. And you can see that there's some 41s and some registers over at the right, so that's a good sign. And in order to figure out where exactly we crashed, we'll basically look at the stack pointer to find the exception record that's been put on the stack, and find like the very top D word or quad word is going to be a status value, and then that next the next pointer is our actual crashing stack address. So we can look at that and figure out where we crashed, and basically be able to load that into IDA or some other tool and take a closer look at that particular code. So because our exploit is a web page, there's some constraints about what kind of characters we have. One thing is the architecture is it is 64-bit, so we need to provide a 64-bit exploit. We can't have null characters. We can't have like greater than or less than. Otherwise, we'll break the page. And also, we have a really strict size limit. If we have 1 byte too large past the return address, we actually will cause it to crash before we even get to returning, like jumping back to our overflowed return address. So we have some constraints that we're playing with. But in order to verify that we actually have code execution in the first place, we'll just do a simple payload that's just nop sled, infinite loop, and then our return address that we're going to jump to. And that works. We basically verified that, yes, we can land in our nop sled, and we are actually really executing instructions on the stack. So we have an executable stack, which is pretty cool, and we can jump to our payload. So we control the return address, but we have a really limited amount of room in this exploit. So one thing we want to think about is like what kind of protections exist in the UEFI environment when we're exploiting something in UEFI. And there's actually some pretty nice things about this from an attacker point of view. Defense, not so good. You're essentially running as ring 0. There's no address randomization. There's no stack canaries. There's an executable stack. There's no memory protection at all. So Alex mentioned a number of Dixie drivers, and when the system is booting up, you could have like 500 different Dixie executables, and these are loaded into the address space, but there's no memory protection between them. So one thing we were thinking about is we have a limited amount of space in our specific overflow, but what happens if we have the rest of the document? Can we just add our payload somewhere else in the document and have it show up? So it turns out that if you start looking at each of the different registers, showing memory, seeing what's around them, near the R10 register, we find a complete copy of the payload. That whatever that document that we returned is also in memory near one of the registers, which makes things a little bit easier for us. And so essentially, we end up having our little payload with a specific overflow just has a little egg hunter bit of shellcode to go find our other payload by starting at R10, decrementing backwards, looking for a specific tag. It's a pretty traditional approach to go find the rest of your code. And if we just append the rest of our payload to the end of the XML document, we can find that on the heap. So we have part of our code running in the stack, part of our code running in the heap. And we can basically have our little egg hunter. In order to debug it, we still have our infinite loop there. And you can use this functionality to basically skip over the infinite loop using move PC to line. And then, because we don't want to step through the entire search, we can just use the run to line functionality. Like, these are all really common operations that you use when you're debugging this kind of payload. And we can basically find our payload and jump to it. So now we have a lot more room, but what can we actually do at this point? Because traditional shellcode won't work because there's no operating system running, there's no libc, there's no kernel, none of this exists yet. But there is actually a pretty rich UEFI execution environment. And there's something called boot services, which is pretty useful, and there's some functionality there that we can use. But in order to actually take advantage of that and build a payload, we need to know how UEFI actually works internally. And so there's a concept of UEFI applications, UEFI protocols. There's the system table, which is a pretty key component. And then there's also boot services and runtime services. Boot services is only available before the system, while it's setting up the system and before it loads the operating system, boot services is available. But once it calls this exit boot services call to signify this is the end of the Dixie phase, and now we're going to start loading the operating system, boot services goes away, and then you only have runtime services available after that. But UEFI applications, they're essentially formatted just as Windows PE binaries. So it's really easy to just drop it into IDA, take a look at it, and figure out what's going on. Instead of having like Unix would have a main application or main function with argv and argc, the initial entry point to all of these UEFI executables, you basically get a pointer to the loaded image that you're running and the UEFI system table. And from the system table, we can find pointers to the boot services table and runtime services table. So those, when you're loading it in IDA, it can be really nice because you know specifically what these particular structures are. IDA even has structure definitions for these, so it makes it a lot easier. These boot services and runtime services are essentially objects with a lot of function pointers and different functions that you can call. Essentially, they're basically UEFI protocols, where the core mechanism within UEFI is this concept of the protocol, where it's essentially an object-oriented programming mechanism where you identify it by a GUID, a globally unique identifier, and there's a boot services call to locate a protocol. So if I want a particular named, or if I want a particular protocol like the DHCP Dixie driver or some different functionality, I can say locate protocol and basically get a pointer to that particular protocol that I can then just call functions in. And it's a really powerful mechanism, but like I mentioned, there's no address protection or memory protection between these Dixie drivers, so there can be some problems with that make things easier from an exploitation standpoint. So the system table contains boot services, runtime services, some basic console input and output functions, and then a configuration table. And the configuration table basically has a little bit more information about the state of the system. And boot services has some pretty useful functions for us, like memory handling, setting up events. You can hook on a particular event. So maybe there's a particular bit of functionality that hasn't been loaded yet, and you want to make sure that your code runs after that happens, and you can hook on a particular event. Protocol operations, like you can register and say, I want to provide this particular protocol, and someone else can call you. But then there's also the ability to load and start a UEFI application. And that's a pretty key thing for our needs. And also exit boot services, which is just basically tears down the boot services functionality and only leaves the runtime services functionality. Runtime services includes things like variable operations. If you have UEFI variables, you would use this in order to read them, write them, make changes. Maybe you can add a variable. It's a pretty powerful functionality. And capsule operations. The intended mechanism for doing updates in UEFI is to use a capsule, and not everybody does that yet, which is kind of why we're here today. But capsule is basically a mechanism where you can have a particular signed blob and trigger this capsule update. It will go into SMM, verify the capsule, and reboot or set the system to sleep. And when it comes out of sleep, it actually applies the update when things are still unlocked. But that's the way things are supposed to work, but not everybody's using that. Some of the useful boot services functions are locate protocol, load image. We have the ability to basically load any Dixie formatted UEFI application, and any UEFI application into memory. And load image actually has the functionality where you can either say, I want to load it from a particular path within a particular firmware volume, or you can just pass it a buffer to memory and say, I want to load a UEFI application from this buffer with this size. And that's really useful. So we'll want to have a load image from a buffer, and then start image. We'll take a handle that we've gotten from load image, and just the dispatch will start executing that code for us. So the problem is, we need to find the pointer to boot services in the first place. I mentioned that every UEFI application gets a copy of the system table when it's initially starting, but that was before we ran into our vulnerable code path. But one thing that's really useful for us is that the standard UEFI application startup code will take a copy of the boot services pointer, the runtime services pointer, and write those to global variables within its application. And because there's no address randomization, we can figure out what those addresses are. So we can even just hard code those pointers, and it just works. So essentially, we're going to end up with a payload that looks kind of like this, where we've got our NOP sled, our egg hunter, and return address in the actual overflow on the stack. And then in our rest of the payload that ends up on the heap, we've got a little copy and decode stub and load and start image shellcode, and then we'll just tack some arbitrary UEFI application on the end of it and basically load and run an application that we provide through our web page that we return to the request. But there was a problem that we ran into, is that when the return address, when we overflow the return address and that function returns, it has just called free on our buffer in the heap. So if we call any functions that will trigger memory allocations, it's going to corrupt our payload and stomp all over that. So that's not what we want. But it turns out that we can just copy our second payload on the heap somewhere else that we've determined is safe, and then that just works. So let me run a quick demo of actually a payload that we put together. Let's see. So here's the ASRock BIOS running. It's standard. So as it's running, it'll go out, retrieve our payload, and we've got arbitrary code execution in BIOS. And this is at a point where the system is completely unlocked. None of those spy protections that I mentioned have been enabled yet, so we can essentially do whatever we want at this point. And let's see. So we can also do a more complex exploit. That example was pretty small, and this one is essentially running a full UEFI shell executable that is about a megabyte. And we did have some encoding issues because we needed to avoid bad characters. It turns out that using MSF Venom to encode your payload when it's a megabyte really doesn't work. So we had to create our own debug stub. So our payload is actually about 2 megs, and we're running a complete UEFI interactive shell. And this is just demonstrating that we have arbitrary size. We can put essentially whatever size application we want in here, and we can use all of the existing UEFI functionality that exists. So ramifications for this. It runs before the spy protections are enabled. You can write an implant to the spy, and it'll survive reboots. The one key point about this is that because we're exploiting code in BIOS at this early point, and like a lot of people will think that TPM will save you, or like the measurements there, secure boot will save you, but it really doesn't, because this does not change the measurements that are actually happening. The TPM and measured boot is only recording what the code is supposed to be running, the code that's in SPY. But because we are getting arbitrary code execution at this point, this doesn't change the measurements. We can provide our own fake measurements from beyond to this point to get up to the point where we can unlock BitLocker keys, unseal them from the TPM. One interesting point is that we do have the ability. So this particular BIOS does have a NTFS UEFI driver built into it. We could use that to mount the hard drive, drop implants into it like Hacking Team Rootkit did. We could also read secrets off of your hard drive and email them somewhere, or we could use the network functionality to bring up our own network connection and send those secrets elsewhere. It does have a full network stack, so we can have a much more complex command and control. Security hardening, like these are all features that have been talked about, but none of this exists in the reference implementation yet. They have been talking about having stack canaries in UDK 2019, I think, but none of that exists yet. We did put together some simple YARA rules so that you can detect this. It's basically just looking for those overflowed fields, and if they're above a certain length, alert. So this was the ASRock one. This is the ASUS one. So there is an ability in ChipSec. ChipSec is a really great tool for exploring UEFI system and even just exploring the hardware of your system. Exposes a lot of hardware debug. It exposes a lot of hardware interfaces. You can do arbitrary memory reads and writes to physical addresses. You can read and write to I/O ports. You can do PCI access. But we've added additional functionality to basically be able to do whitelisting and blacklisting of EFI binaries within your system. So you can use ChipSec to read the contents of your SPI, generate a whitelist, and then maybe after you've traveled to somewhere that you think the maid might do something sketchy with your system, you can then check your system against that whitelist and see if there have been any changes and if you have any new EFI modules that you didn't have before. So this is a really great tool to take a look at, and even beyond the whitelisting and blacklisting functionality. And so some conclusions. Firmware is already complex, and it's highly privileged, and people keep adding more network surface to it. So the remote attack surface is just getting bigger and more complex. And BIOS is hard to update, so a lot of people don't update the BIOS. And ironically, making it easier to update your BIOS adds vulnerabilities like this sometimes. So I think that's the end. Any questions?